Listo.
Greetings, everyone. We are from the Faculty of Engineering in Electricity and Communications from SPOL, and this is our Integrator project that we do in order to acquire the title of engineer. As you can see from the first slideshow, our project is the smart tree implementation for the creation of greenways that help mitigate the heat footprint in Guayaquil. Our integrants are Luis Macias and myself, Miguel León. Our tutor is the Dr. Washington Velasquez. Well, the problematic of our project is since a metropolis like Guayaquil possesses a high-density urban zone with scarce green areas, besides the abundance of commerce and traffic, it generates a high footprint. This can also be attributed to the types of materials used in this environment, and thus impacting the well-being of its citizens. The justification of this project, it's mainly to allow green areas like parks to be interconnected, amplifying the ecosystemic services that these areas help, like mitigating the heat footprint and providing shadow and capturing carbon in order to preserve the health of its citizens and, well, remove walking and recreational spaces in these areas. Our objectives are basically the main objective of this project is to implement the smart tree using IoT and cloud computing processing for the creation of the greenways that help mitigate the heat footprint in Guayaquil. These can be achieved by following the specific objectives, like identifying the parameters of the smart tree that allow the care and control of the trees within the greenway, to develop an embedded system with cloud computing that obtains, processes, and displays the information on the mood of the tree, and to establish the number of smart trees required for the design of the greenways in the streets that we have previously chosen as a study. So our theoretical framework, by the pictures that you can see, are encased in four main aspects, which are the urban heat island effect, which is urban the heat footprint itself, the greenways, what is a smart tree, and IoT as a paradigm itself. And so the urban heat island, or also known as urban heat footprint or urban thermal islands, are mostly a thermal gradient that is observed in densely populated urban spaces such as cities or metropolis and the rural periphery, with a concentric spatial pattern focused more on sectors with great infrastructure predominates. This is the contrary to green infrastructure that we are going to focus in the greenway itself. So the greenways are basically green areas or green infrastructure, as previously said, that expand the ecosystemic services that parks or other bigger green areas give, as previously mentioned, shadow, carbon capture, purifying the air, and, well, helping to better the air quality of the surroundings. And smart tree is basically an organic vehicle, organical agent that is a tree with the combination of sensors and controllers that help monitor environmental variables that can be used and in order to make decisions and taking care of the tree itself. Finally, what we have is Internet of Things that, for example, defined by Cisco Internet Business Solutions Group, it was the point in time where more devices were connected to the internet than people, referring to devices that are not handled all the time by an end user. It can also be seen as an emerging architecture based on the global internet that facilitates the exchange of goods and services between supply chain networks, and that has a major impact on the security and privacy of the sectors involved, which is an extension of machine-to-machine-like communications expanded to the internet itself. My partner now is going to continue with methodology.
Greetings, everyone. The chosen methodology was design thinking, as you can see here in the picture in the top. It has 5 steps, and the empathize and define steps were defined before because it's part of the research of the project. And we determined that the variables and the environmental variables that we use to achieve our principal objective is the temperature, humidity, air quality. So continuing with the next step, the following architecture was created. As you can see, it consists in 4 parts: users, app mobile, Blink Cloud, and smart tree. Users are the actors of the systems. In this case, is the administrators or other users that want to visualize the environmental variables. The app mobile is the user interface that we use to visualize the data that is connected to Blink Cloud. Blink Cloud is a REST API-based platform for IoT project that allows you to connect your devices to its cloud to display data. And this is connected via Wi-Fi to ESP8266 module in the smart tree. Okay, the smart tree is the prototype that carries the sensors and controllers in charge of data collection, processing, and sending the data to the cloud for visualization. Next, please. So we have this the design and implementation. The schematic shows the connection of the different sensors. As you can see here is the bottom are the devices that we use. And the protection is these boxes we have to develop our prototype. And the schematic shows all the pins that devices needs to send in data and connect it to the controller. Okay, next please. And this, in the left picture, we have the assembled prototype, how the devices are located in the prototype. We use LSD screen, air quality sensor, temperature and humidity sensor is a DHT22, and FC28 is a soil moisture sensor for the project, for the tree, that indicate when we need to irrigate the tree and when not. The power supply of the project is a solar panel that charge the batteries. The batteries supply the controller and the other devices using the system. On the right picture, you can see how the data is visualized in the interface, in the user interface. So we have this type of graph for the different variables: temperature, humidity, and CO2. This means air quality. The bottom of the picture, you can see the message where indicates when needs the plant to be irrigated or not. Next, please. As results of our project, we show those points in the left picture. We have two types of data points. The reference in the parks and the measurements of the streets, the variables in the streets. So we took a variable different types because we need a reference to compare it with the variables in the streets. The pictures are shown of the different location where the prototype were measurements will measure the variables. So the reference data point in the left picture shows the average of humidity percentage. As you can see, it vary between 70%, 33, 34, 74%, because the vegetation of the parks. The temperature is average between 28 or 27 degrees Celsius. The quality is good because the harmful gases is, you can see, is the measure is in ppm, part per million, and it around between 310% ppm and 350 ppm. The red pictures shows the data collected in the streets. As you can see, the temperature, the average of temperature is 32 degrees. This is because the car traffic and the nature of the environment in the streets is directly with where the heat footprint is concentrated. And the humidity is between 40 and 50%. That indicates the humidity in the streets. The average of air quality, you can see, is 50%, 500%, 500 ppm, 600 ppm. Is this because we have more harmful gases like carbon dioxide, other gases that is in this environment of car traffic. Next.
Okay, well, now as conclusions and recommendations that we have acquired within the development of this project, we have said that, for example, by the theoretical investigation and recompilation of data, that with the environmental variable results of the measurements, we can corroborate that the presence of green infrastructure reduces the thermal sensation when comparing the temperature of the gray infrastructure, as my partner clearly represented in the previous slide. This is true added to the vehicular traffic and the emissions of harmful gases against the temperature that the green areas contribute. Since the green areas make a significant difference in the thermal sensation, and that also it captures carbon, lowering the perpetuity of heat within the environment and the thermal sensation in the streets. And that can be achieved with the presence of trees within the selected streets. As you can see, as was shown in the previous slide, the minimal temperature was 27, 28 Celsius degrees when trees are in the environment, and these increments in about 6 to 7 Celsius degrees when it's there are no trees or green spaces available in the streets. We also, thanks to the theoretical framework and state of the art, we were able to identify the parameters of interest for the happiness of the tree that we previously mentioned, that are temperature, the relative humidity, the air quality, and the soil moisture of the tree, to provide the sufficient information to meet our first objective of the project. Also, knowing that the Guayacan, that was the tree chose for this project, is a tree that lives in hot and tropical climates, it can also be stress induced to high temperatures because it has a tolerance limit that is, if I'm not mistaken, around 29 to 30 Celsius degrees. And when it's good to determine, it was good to determine when was the perfect time to irrigate it in order to not overheat the tree and harm its development. Also, the embedded system prototype proposed main functionalities were achieved, which is cloud computing and the showing of the information within the tree and through an application and web panel. This is the physical prototype and the user interface displaying the big platform. Control, power, and sensors devices were sufficiently protected in accordance with the limitations as we found in the project, and comply with their operation in the different environments of the city in Guayaquil. Therefore, completing our second objective. And also, the number of trees depends on various factors, such as current legal regulations, that is, legal processes related to the tree planting and urban areas. Also, the species, because that would determine the size that it would have when it reaches another adult state. And its tree neck, because with the tree neck and its size, as I said, we can determine the spacing between each tree, and it can not interfere with traffic lights as well as electrical wiring or any other type of signal that helps a good transit within the city in order to prevent accidents and a long-term green infrastructure benefit. And well, as recommendations, we have, for example, to use nickel metal hydrate because it allows us to get more energetic density, and it has a better power efficiency than the lithium batteries. Also, in order to charge this type of project, it is recommendable to use a P-channel MOSFET and a Schottky diode to make an automatic switch between the load, which is the main circuit, and the power source, which is the solar panel, in order to charge the battery and keep functionality at the same time.
Okay, for future lines, we think needs the project needs an own app mobile application mobile. So for the Blink Cloud solution, it's a free solution that have very limitations. So with our own application, we can show more specific instructions or more specific graph to show about the data. As Miguel said, we can use an OLED LCD screen because LCD screen that we use in this project consume more current, and it could be worse to the project because the batteries consume very high. The LCD screen, the OLED screen is more effective in the power consumption. The device used in this project, we use commercial devices that is not specialized to use to power all the devices we use. So in the right picture, we can see an integrated, a very integrated for the charge of the batteries using the solar panel. That we have to use a Schottky diode and PMOSFET to switch the load and the charge of the battery, and this integrate do the same, but his own, and so this is, thanks.
Thank you.